Okay, now let's learn about something very interesting and surprisingly less complex than the PSEN. PSEN was a bit tricky with that buffer or overhead and so on. But I wanted you to know about it because PSEN and SN are very common. Now we're going to learn something of crucial importance when it comes to performance, called collective operations. So we can start swimming around collective operations, thinking about synchronizations. With MPI SN and MPI receive, now you know the difference between synchronous and asynchronous. With a synchronous one, you know that as soon as you return, the recipient has your message. So that can give you some sort of synchronization. However, the same way that in OpenMP, sometimes we like to have all threads reach a certain point before we move forward. In MPI, say, we may want to have all our MPI processes reaching a certain point in time in the code before we all move forward. We can call MPI variables. And we just need a communicator we're talking about. In C or Fortran, nothing surprising here, just the MPI command. This is the example of what we call a collective operation. Collective operations must be called by every single MPI process in the communicator considered. So if it's MPI Commonwealth, every MPI process in MPI Commonwealth. One MPI process not calling it, it's a guaranteed deadline. Your program will be stuck there forever. Okay? So what are we even learning about collective operations? There's this one for synchronization, but most importantly, we have many collective operations for communicating patterns that are quite common that we know about. And typically, not only do they take care of actually making these communications happen without any mistake, but they are also, trust me when I say this, they are also highly optimized behind the scenes. So we're going to see 4 collective operations. The first one is good old broadcast. You have a message that you want to send to all your MPI processes in one go. You know how to do it. MPI send, MPI send, MPI send. Or you can go with a broadcast. Again, as I said, as soon as you know MPI send, MPI receive, you can do everything you want. This is just to make your life easier and your program much faster. It's a broadcast, so we call that MPI broadcast. Broadcast is too long, so MPI bcast. You can recognize the structure of MPI routines here, always the same. The buffer we want to send, how many elements in this buffer? What's the type of an element? Editor rank, which is what is the rank of the MPI process that contains the data to broadcast to all MPI processes? And the communicator we're talking about. Nothing new when it comes to bundling, whether in C or Fortran, just MPI data type and so on. Okay? So the broadcast, very easy to do. Now we're going to learn something called, so that's already the end of a collective operation. See, so that's extremely simple, but very powerful. Broadcast, done. We're going to learn one called scatter now. Scattering is when you have an MPI process that has multiple elements and it wants to scatter them, to distribute them across multiple MPI processes. This time it's no longer giving the same element to all of them, it's giving different elements to each. But always the same number to each MPI process. If you want to learn how to send different numbers to different MPI processes, you need to come to a more algorithm. For the time being, this is what a scatter looks like. The routine might seem a bit scary at first because there starts with quite a few arguments up there. But actually, if we take it step by step, it's not harder. First, the buffer we want to send. So all these colors here. The buffer containing all the colors. How many elements per MPI process? So here I have a buffer of 4 elements. Each MPI process will receive 1 element. What's the type of an element? MPI A, MPI, everything you want. Then there's the receive part. Because this information is not useful for the sender, but the receiver have to say, oh, and I will receive that as an MPI end. Okay, let's start. Yes, when you are, since this is a collective operation, every MPI process must call it, but not every MPI process will be the emitter, will be the one sending the data. Everybody but one will be receivers. They don't have any information to pass there. So they are not even relevant. They are not significant, as we say. So you can pass no, zero, MPI into what you want. On all the receiver MPI processes, this will have no importance. Then it doesn't have all the receiving outputs, which are the same as the one you've seen in MPI receive. Where do you store this MPI end you're going to receive, or this, how many MPI chart flows? How many do you have? And what's the type of an element, as always? Then we have the root, which is what's the rank of the MPI process that's going to scatter all this data? As always, in these collective operations, we need to know who is the MPI process that's going to initiate everything. And finally, the communicator. Okay? When it comes to actual types in the bindings, whether in C or Fortran, nothing new here. You already know MPI data type, you already know MPI code. The only difficulty is just to go through this list of 8 arguments, but each argument is not very hard. Fortran looks scary because it looks like a full string, but again, there's nothing different here. Type star integer, MPI data type, type star integer, MPI data type, you know that. So scattering is when you have a list of elements that you send across MPI processes. There's the reverse of this called gathering, which is where every MPI process has some data that you want to collect and to aggregate, concatenate on a given MPI process. So the way to do this with scattering, it was called MPI scatter. So to do gathering, it's MPI gather. So far, so good. Many arguments, but it's exactly the same list actually. Very reverse. How many elements, what's the buffer containing the elements you want to send? So the blue or the red or the yellow and so on. How many in there? What's the data type? And now for the receive part, only significant on the MPI process that will receive everything. If you just send, you can pass no here. How many elements receive per MPI process? So if we have 4 MPI processes sending 1 element each, here I must not say 4, I must say 1. It's how many elements per MPI process. And then the data type of the elements received, and exactly like MPI scatter, which is root for the rank of the root MPI process, and the communicator. Once again, the bindings have nothing different. They are really copy-paste from the scatter, whether in C or Fortran. Okay? Now the last collective operation, because that's already the end of broadcast, scatter, gather. Here is not the collective operation that can allow you to scale to. When I mean scale, I mean efficiently scale to large number of MPI processes, even if you have many other techniques and leverage. That's still the really fundamentals one. Without this, you can forget large-scale processing. There's another one, a big one, for reductions. So reductions is when you have multiple elements coming and somehow you reduce them, taking the sum product, minimum, maximum, or something you design yourself. In MPI, you can design your own reduction operation. Too advanced for today, you can do it. Not that hard. When it comes to the actual signature, not much different. What's the buffer you send? What's the buffer in which you receive? It only makes sense on the root as a way. How many elements are we talking about? What's the data type? What's the operation? I'm going to come back to this one in a slide. The rank of the root MPI process, the MPI process that will have the result at the end, and the communicator we're talking about. Okay? Whether it's C or Fortran, again, nothing new now. You know everything where you go, so nothing new. Now, I mentioned the operation, and typically we'll do a sum. So MPI underscore sum. Easy. But you may say, yes, that's quite limited to like sum. I may want to do something else than sum, which is why we have other reduction operations. Exactly like in OpenMP, you have some choices. Again, if that is not sufficient, even if we're not covering it today, you can define your own reduction operators. But with all this, you're good to go for this exercise here, where you will get to analyze all of them. You will have to get to practice these. And then we'll finish this session with the non-blocking operations, which is another big thing in MPI. So we have MPI process 0 that has an information that needs to be sent to all other MPI processes. So in other words, we need to broadcast it. So MPI broadcast something. What it is we are broadcasting, right? Which is one MPI. Let me check the
Oh, yeah.
So, yeah, we have just the editor rank, which is my rank. And then if I do this, what happens? If I try to compile and run my program here, what happens? Do you think? Will all MPI processes call this function? Only the MPI process whose rank is my rank, or whose my rank is 0.
Yes.
So it means not everybody is going to call this routine, which is a collective operation, which means guaranteed deadlock. Because MPI process 0 will wait for everybody to call this routine, but they will never call it.
So you put it outside?
Yes.
Yeah.
Because you are facing deadlock, your program was stuck. So that's why. Okay, we can quickly do a check. Here, root rank equals that. Let's save some time here. It hasn't yet. Wait. Okay, rank equals 3.
So just a note, right, that the codes don't, each rank can run different things. So if you have the MPI bcast here for rank 0, but somewhere down the line in some other function, there's an equivalent MPI at the same time of bcast, the appropriate tags and something for all the other ranks, that's fine. They just have to have something that matches, but they don't have to be in the same portion of the code. Okay. So if you have if statements, if you had like if rank equals 0 and you had that bcast, you could have every other one do lots of other stuff and then stick in the appropriate bcast much later on. So what would happen is rank 0 would hit the barrier, saying, I gotta wait for everybody. They would do tons of stuff. They would also do the same, look at the same bcast, essentially, like have the same sort of type of communication. They would all then process and then keep going.
So as long as they're all in the same collective operations.
As long as they all are encountering the same collective operations, the same barriers, the same, if you have blocking, if you have a blocking send and a blocking receive, if they could be completely different parts of the code, they could be doing very different things, but as long as there's a match, then that's fine. But it also means that if you are not careful and you have sends and receive and bcasts, which can look the same, but are not the same in an encounter, then you get stuff being sent that is then not acceptable.
So that's for the broadcast. Now we have a scatter, because now that we have, we know who is going to be the root of everything coming. We need now to scatter the values we have, all the MPI processes we have. So this, how to do that? We know that it's calling the scatter. So this here, So this way we can do it step by step. So what is the buffer from which we're going to send everything? It's from which we're going to scatter everything. It's values. Okay, make sense? It's this buffer here that we're going to send, and we're going to receive the little scattered part in this one. So how many elements are we going to send per MPI process? It's this count here. Yes. What is the type of what we're sending? Int, yes. How many are we receiving? How many are we receiving? No, where are we going to receive them? In my elements. How many are we receiving? Well, count. So this count 2 here, okay. What's the type? Well, again, it's an MPI we're receiving. Who's the root? Well, the one that has the root rank. And which communicator are we talking about? MPI comma. Okay. Well, now we can have everything processed quickly. I'm trying to get a bit quicker so that I can have enough time to do the non-blocking. So I received this and this. So my elements, 0, my elements, 1. Okay, so you see they received different values. Remember they're random anyway. But they're all under 20, since we're doing a modulo 20 in the in this value here. That makes sense. Now, we have all received our values and we do some calculations and we get some local result, okay? But we want all these local results to be reduced in a single big result on the root MPI process. So for that, we're going to need the reduction. I'm going to get the prototype from there. To do the reduction, we have the MPI reduce. Okay. Where are we going to receive it? In the value, in the variable called total? No, sorry. That is for the receive buffer. We're going to receive it in total, but we're going to send it from my total. So every MPI process sends from my total, and it will be received on the root MPI process in the variable called total. How many elements per MPI process? 1. We just send 1 integer each. So that means it's an MPI int, by the way. And we do a sum here. So MPI sum. Make sense so far? Yes. The root, the rank of the root, we know it. It's root rank. And the MPI communicator. Today it's only MPI com. Well, n. Okay. That means. I swap the 2 again. No, not the same. MPI reduce the send buffer, the receive buffer, the count data type, the operation, the root, and the communicator. And it's not happy because
You missing pointers.
Because then he thought it was a function declaration. Okay, here we go. Done. So here we've used 3 different collective operations. Again, that's just a lot of arguments, but they're simple arguments. The only trap, that's why I really try to make it clear, when you do a scatter or a gather or reduce, is the number in the count. It's the number per MPI process, because it's extremely tempting and very intuitive to then say, oh, I'm going to scatter 4 elements, 1 per MPI process, so then the count is 4. No, the count is per MPI process, so it's 1 per MPI process. That's the only trick, right? If you're here this afternoon, I'll show you that there were multiple implementations for any collective operations, sometimes hundreds. Anyway, that's for Saturday. Quickly non-blocking, because that's a very important one as well. when we are calling an MPI routine, send, vsend, rsend, receive, reduce, scatter, everything so far is blocking. It means that it waits for completion to be reached before returning to the execution. Which is why I was mentioning this with synchronous and asynchronous. I was already using the term completion, because then what comes next is non-blocking. In non-blocking, what happens is you don't wait for the completion. You return immediately. In other words, we're going to see non-blocking versions of send, for example, like send or vsend, the one you okay, receive. Receive, the completion of receive is when the message has been received. Okay. You can do non-blocking receive, so say, okay, start receiving the message, I'll do something else in the meantime, then I'll come back to you later. And then when you come back later with this extra operation here, extra operation. I don't know how I managed to do this. That's pretty hard to do later. Anyway, you have an extra operation to check if that operation you started a time ago is now complete. It can be useful for two reasons. Bypass deadlocks when you want, for example, when you have two MPI processes and they want to exchange a message. So it's like, do we send both of us together first, or I send first, you receive first, and you send then, and I'll receive then? This coordination can get really tricky when you have 200, 300, 400 MPI processes in 3D couples and everything. So you can just say, okay, start sending, non-blocking, and I'll wait. So the send will be done at some point somewhere. And more importantly, for the overlapping computation and communication, because if I send a long message, a big message, I send it and I wait for the message to be sent before I do something else. Start sending this, I'll get some computing power. I'll get my CPU running rather than waiting for the network to transfer the data. That can be very useful. And they're very easy to use because you already know MPI send, send, and so on. To use the non-blocking version of anything, it's always an I at a time because it stands for immediate. So MPI I send, I receive, I are sent, everything. Note that yes.
It's often said all non-blocking.
No, so that's why I really go for the right terminology straight away. With MPI vSend, it's asynchronous. But in MPI, there's this distinction between asynchronous and non-blocking. In JavaScript, everything is asynchronous, for example, where sometimes we don't know what. Here, the MPI vSend, I wait for MPI vSend to tell me I'm complete, whatever that means. MPI vSend raises a flag when it copied the buffer. MPI I vSend, I tell let's say we have someone who's MPI vSend. I give the message I want to send, and I say, okay, buffer this, I'll come back later. I don't even wait for that worker to tell me it buffered. I'll just say, buffer that, I'll come back later. The resulting consequence is I must not modify that message or that buffer that I want to send, whether it's synchronous or asynchronously, until it has been sent. So until I checked, I came back later and I checked and said, okay, did you complete now? Okay, cool, I can use the buffer. Because if I modify the buffer before having checked that, maybe the copy hadn't happened yet. So the signature compared to the send is identical, except the final one, which is the request. This is the object we're going to use later to come back. It's like a little tag, if you want, a little QR code. We can come back to scan it to see if it's finished. So all the first ones you know already, buffer, count, the type recipient, tag, and communicator, all the same. Request is going to be that little tracker you can have. The type is MPI request, as always. Data type is MPI, data type, status is MPI, status, request is MPI request. We make your life really easy here. And the Fortran version, MPI request too. Okay? I receive, same thing. Everything is in common with MPI receive, the blocking version, except the final one, request. So here. In C or in Fortran, same thing. So that's the first part. And that's so it works for really good. We are at the end anyway. That's the first part. We initiated our non-blocking operation. Now we did some computation, we did something, and we want to check if it's finished. We're going to call an extra function called MPI wait, where we're just going to pass the request we want to wait on, and the status. You know, when you do MPI receive the status, same thing. And that is going to block until the corresponding operation is finished. Okay, so that's where you have your initial synchronization. Either it's already done by the time you call it and you call the instance, or it wasn't done ready and you will wait this time until in vSend until the message is copied. Okay, now I can go back. Okay, make sense? When it comes to the binding, nothing surprising. We're talking about a request and a status. So the types are MPI request and MPI status. Nothing surprising here. That we won't do right now. And that we won't do right now. If you want, if it's not too late for you online or in person, which I totally understand, if it's too late, don't worry. If you want now or later, you can try the exercise 6, where the idea is to practice this non-blocking.